Hello and welcome back to my YouTube channel, a place where you come to learn about numerical methods. In this video, we'll be learning about Newton-Raphson method. Here, in this method, we make an initial guess and use the derivative information at that point to refine our guess until we reach to a converged value. Let us first refresh our basics. So, if let's say I have a linear function and I want to find the root, it is very simple. But for a non-linear case, it is not so straightforward. So what we'll do, we try to approximate a non-linear function by its linear counterpart. So we'll calculate the functional value and its derivative at the guess value. Then using that, we create a tangent. And wherever this tangent intersects the x-axis, that will be our refined solution. We repeat this process until we reach convergence. And this is the crux of the Newton-Raphson method. Now let us try to visualize this graphically. So let's say I have a nonlinear function f of x. I guess a value a, which is x0, 0. Now the corresponding function value is x0, fx0. I just draw a tangent at b and that intersects at c, that is x1, 0. Now if I closely look at triangle ABC, clearly it's a right angle triangle and the angle BCA is the derivative at point B. So if I want to rewrite this thing as a formula, so this will be f prime x0 is equals to fx0 divided by x0 minus x1. By some minor algebraic manipulations, we get to a formula where x1 is equals to x0 minus fx0 divided by f prime 0. This is the Newton-Raphson formula. This is nothing but using tangents to iteratively approach to a root. We can keep this formula handy for our further discussions. Let us see how can we implement Newton-Raphson method graphically for different types of function. So for a quadratic function, it is very simple. We draw tangents to a point and wherever it cuts, that is my new guess. Again, repeating the same process, we see that after iteration by iteration, we are getting closer to square root 2. Iteration 2 and iteration 3 see a very small change, while iteration 3 and 4 will have negligible change or no change at all. And hence we conclude that we have converged to a value. Now for the second example, we take a cubic function. Here the cubic function with the initial guess x0 equals to negative 0.5 is taken. We draw a tangent to it and it cuts the x-axis at minus 1.2051. Now we go to the corresponding point on the function, draw a tangent again, and now it cuts at negative 1.01. We repeat this process for 2 more times until we converge to negative 1, which is the root of this function. Enough with the polynomial equations, because we know polynomials are very simple to solve. Now let's go to a transcendental equation where we have functions of x which are not monomials. So here we have an exponential function with an initial guess negative 0.3. We see that within 3 iterations, we are able to converge to a value which is very close to the actual root. So we can say that not only polynomials, even transcendental equations can also be solved iteratively by using Newton-Raphson methods. So now let's quickly move on to MATLAB and try to implement this method numerically. So we create a function, Newton's method, which takes in the following input and returns the root of the input function. The below algorithm has already been given in the Wikipedia webpage. So first, what we'll have the input as the initial guess. Second, we want the function handle, for which function we are calculating the root for. Third, we want the derivative function. Then we decide for a tolerance that serves as the stopping criteria, so that if the subsequent guesses are less than this tolerance, then we say that we are converged. Then epsilon is the threshold below which we don't want the derivative to go. Then the last input will be the max number of iterations we are trying to solve for. Then the output will be the root. if the method converges, or NaN if it doesn't. So first we start with the predetermined value of root as NaN. So that if the method doesn't converge, it will return that value. Now we go inside a loop where we are moving from 1 to the max number of iterations. Then for each loop, we calculate the function value and its derivative. First, we give a check that the derivative value should not be too small. Then if it doesn't, then we move on to the Newton formula. By using Newton formula, we create the new guess. Now we check for tolerance, whether the new guess and the old guess are close enough or not. If they are, then the method seems to have converged. If it doesn't, then we use the current step value and update it in the loop. So now for the next step, the current value will be taken as the initial guess. So we do this updation and then print the statement that current iteration, the value of x was this. Then this loop is restarted. So if by the number of max iterations we are unable to converge to a root, then the final message will pop up that with the max number of iterations we were unable to converge. Now this code has already been published on my GitHub page. You can download it from there, and then using this file you open it, and then there is this format where you can use to calculate a root for a function. Here we first define all the input parameters that are required for a function to run. So we'll have our initial guess, the function definition as function handle. This @x is very important while defining the function, and also this dot before any multiplication or raising a variable to a power. So this is very important. Please take care of this. Then after defining the function and its derivative, we define the tolerances. Here I have taken 1e minus 8 and 1e minus 10 as my tolerance in epsilon, and the max number of iterations that I am trying to solve for is 100. Then we call in the function by using all these inputs to solve for our answer. So now I will give this a run. So as you can see, with all these outputs given on the right hand side of this MATLAB file, these are all the inputs that we have given, and this shows at which iteration what was the value of x. So you see that after 3 iterations, it is trying to converge to the square root 2 value. So after 5 iterations, it says that it has converged and the final root value is this. And below it shows how much time it takes to solve. Now let's play with this code. Now I'll change the initial guess from 1 to 0. I'll give it a run again. So it shows me a fatal error that derivatives are too small, because as you can see in the derivative part, it is 2 times x. So now we take a value which is slightly more than 0, and we see that our method converges in 15 iterations to the same square root 2 value. Now let us take a value which is very far from square root 2, let's say 1000. So now still you see that within some minor iterations, it is able to converge from a very far off initial guess. This is the characteristic of Newton method for convex functions. Even though you are very far from the initial guess, you will still be able to converge in very less number of iterations. This shows you the power of Newton-Raphson methods and its quadratic rates of convergence, that we are able to converge to a solution which is very, very far from your initial guess. So now let's change these function values. Instead of this function, quadratic function, I take a cubic function from here. So I just copy paste it there instead of those function values and the initial guesses. And now I'll take this function value and the initial guesses. With the initial guess at 2, when I solve this function using Newton-Raphson, I see that it converges in 9 iterations. So now I'll just again play with some other initial guess. So now what I'll do, instead of 2, I'll take 2 lakhs. When I'm doing 2 lakhs, you see that then also it is taking only 41 iterations. Although you see that we are very, very, very far away from the actual root. Now I change this value to 1. Now my initial guess is 1. Then I'll give it a run. So just remember this root value. And after giving initial guess as 1, I'll give it a run. Then you'll see that my Newton-Raphson method oscillates between 1 and 0. And it does not converge. So why is it so? The answer to this oscillation lies in the function itself. So this is the function plot. So now if I want to draw tangents at 0 and 1, you see at 0 the tangent cuts the x-axis at 1, while the tangent at 1 intersects the x-axis at 0. So clearly your Newton-Raphson method fails here. So it says that some typically behaved functions at some particular guess values can see oscillations. And even though we perturb the value by some small value, we are still unable to converge. And even so, now let's take a value which is less than 1 and greater than 0 in between this point. So at this bottom point, if I take the value as 0.5 as my initial guess, you'll see that now it converges. So you see that if you are in the right space, if you are with the right initial guess, then you can actually converge to a solution. Otherwise, you can't. So sometimes Newton-Raphson method diverges, and this is one of the examples. So you have to be very cautious about what is the initial guess that you are taking. You should have some idea about what is the nature of the function, whether it contains long valleys or whether it contains some oscillatory behavior under which you can get caught by your Newton-Raphson algorithm. Otherwise, for convex functions, Newton-Raphson is the best possible method out there. So to conclude, if a function locally can be approximated well using its linear counterpart by using just the functional value and its derivative information, then Newton-Raphson is the best method. Each iteration will improve the guess significantly. It is particularly very useful for polynomials, exponentials, and trigonometric functions. And the convergence is very fast, typically quadratic. But we cannot guarantee global convergence for general functions, and sometimes the method fails if the derivative information is bad or the function is not differentiable. For more such interesting videos, please stay tuned.